Hello, ladies and gentlemen. We will look into three problems that we discuss in foundation videos. Finding the maximum number, finding the longest common prefix among group of words, and palindrome number. If you are new to this channel, my name is Komil. I've been software engineer and teacher of programming for over 2 decades. And I've seen beginners struggle when they face new problems and don't know how to use known structures to solve that problem. That's the thing we try to fix here. Let's jump into it. Let's start by defining a list of numbers. Now we have a bunch of numbers to work with. We already know how to access individual items in the list. So let's print the first and second numbers. Good. Now we can ask a simple question. Is the first one bigger than the second one? Yes. So one possible way to solve the problem is this. Compare the first number with the second number. Keep the larger one. Then compare that result with the next number and continue like that until the end. So if numbers 0 is greater than numbers 1, we keep the first element as the current maximum. Let's create a variable to store that value. This variable will always keep track of the largest number we have seen so far. Then we continue. We compare again and again and again. So the idea is incremental. At first, you may imagine it like this. Compare element 0 with element 1, then 1 with 2, then 2 with 3, and so on. That suggests a loop. But there is a small issue. If we want to compare two specific positions in the list, then we need to work with indexes. Can we make it simpler? Yes. Instead of comparing neighboring items, we can compare each number with our current maximum. That is much cleaner. Now we don't need to think about pairs like 0 and 1 or 1 and 2. We just say, for every number in the list, compare it with the current maximum. If the new number is bigger, replace the maximum. That's it. So now the logic becomes much simpler. Let's run it and print the result. Good. Now we have the largest number. And notice something interesting. If we reverse the comparison, then instead of keeping the larger number, we keep the smaller one. And that means we get the minimum instead. So by changing just one comparison, we solve a different problem. Now let's try another way. We can use the max function. This is a built-in function in Python, and it gives us the result immediately. Very nice. And there is also a third way we can try in this video. We can sort the list and then take the last item. That also gives us the largest number. So now we have three different solutions. To compare them properly, let's generate a large random list. For example, 10,000 numbers between 0 and 1 million. Then we repeat each solution many times, so the timing difference becomes easier to see. To measure that, we can use the time module. We record the time before the code runs and the time after it runs. Then we calculate the difference. Calculating process time for the first solution. For the second solution, using max function, and for the first solution using sort function. Now let's look at the result. The winner is max. Then comes our own loop. And finally, the sorting solution. At first, you may think max feels like magic, but here we need to separate two important ideas. First, big O. Big O is about how the amount of work grows when the input gets bigger. Our own loop checks the numbers one by one. So it is O of n. The max function also checks the numbers one by one. So again, it is O of n. But sorting does more work because it arranges the whole list. That is typically O of n log n. So in terms of algorithmic complexity, our loop is O of n. Max is O of n. Sorting is O of n log n. That means, for this task, the loop and max are algorithmically better than sorting. Second, real speed. Now, here is the interesting part. Even though our loop and max are both O of n, max is usually faster in practice. Why? Because our loop is written in Python itself, and Python runs it step by step through the interpreter. But max is a built-in function, and built-in functions are highly optimized internally. So the key idea is this: same big O, different real runtime. Big O does not tell us the exact speed. It tells us how the work grows as the input grows. So for finding the largest number in a list, the manual loop is great for learning. Max is usually the best practical choice. And sorting plus, taking the last item, also works. But it does extra work. And yes, in practice, sorting can still not very slower than your own beginner loop because sort is also a built-in operation and is implemented very efficiently. So if your goal is to learn the thinking, write the loop yourself. If your goal is to solve the problem in real Python, use max. And this is a very important lesson. A built-in function can be faster than your own code, not because the core idea is different, but because the implementation is better. Okay? Now let's move on to the next problem. Finding the longest common prefix among a list of words. Okay, let's continue with the second problem, with the second example, where we want to find the longest common prefix among some words. Here we have a list of words, so we just want to find the common prefix. One way is to check the first character of all words in the list and check whether they are common or not. Then continue with the second character for all words, and then third and so forth. In this way, we actually need to check all of the words in every iteration. Also, we need to check all of the characters of all words, which is actually very rare that we will have a prefix that is common for all words, because words are different. We need to find a simpler solution here. Another way is to assume that our initial prefix is the first word. Now, our prefix started to be the first word, and then continue to compare other words with this prefix and see which characters are common. Based on that, every time we update our prefix, I think this way will be better. What can we do? First, we need to be able to access every word. Let's see if I write this loop. Can I access all words? Yes. So in this loop, I can actually access every word of the list that I have. That's correct. Then, for each word, we need to access individual characters. So we need another loop inside that loop. Now we access the word, which is every time a word from the list. So for that, we will access the characters and the corresponding index. Let's see if it is working properly. I, D, X, and C, H. Yes, absolutely correct. Now, this is the first word with the corresponding positions, indexes. Then we have the second word. Then we have the third word, and so forth. That's correct. You can see here that I'm checking my program in each step and trying to get the feedback, even if my code is not complete. I'm trying to get the feedback in this way so I can be sure that my program is actually going to the right way. Here now, because in this way, it's easier for me to write a better program and be with less bugs. If I write 100 lines of code and then try to run the program, and if there is a problem in our program, it would be much more complex to find the bugs because it's 100 lines. In this way, gradually I check the program to make sure that it is correct. Now, here in this stage of the code, I know that I am accessing individual characters for each word. Here, I can check the prefix characters with my individual words in the list. For example, if the first positions are the same, I don't need to do anything. I will continue with the second, then the third and fourth, like that, until the moment that they are not the same. Here, for example, the character O and U are not the same. In that case, I should do something. I should update the prefix because the prefix is no longer the whole word of common characters. It's only 4 characters. So that's the thing that I need to do. If the prefix in that special position, starting from 0, is not the same as our word, it means that I need to update the prefix. Instead of this, I can easily write CH because CH here can refer to the same character in that position. So if they are not the same, I need to update the prefix. I can either use word or prefix because it doesn't matter. They are the same until that position. So I'm writing from 0, selecting from 0 to the IDX position. The position, now that they are not the same, here for example, but we know that the IDs won't be included, so it's correct. It means that it will keep the characters until the position before this IDX position, so it should be correct. And after that, do we need to continue with our searching of the characters in that word? No, we don't need it. We already did this before, so it's enough. And this break here will break this loop. Okay, let's see the results. Okay, we have an error here. What is happening here? It's not so clear. It's a string index out of range, so it means that something is out of range here. To check that, I can actually add something to this program to check the output. To prefix in each iteration for each word. Okay, I can see some outputs here. So it is correct the first time. Our prefix is common, and then after that we know that it will be shrunk to only 4 characters. After that, because of this P in this word computer, and it's different from M here, it will be shrunk to com, and then it will remain com. What is happening here? Now, after these 3 steps, we have the error. Until here, everything is correct. But here, when we come to this step, something is wrong. Let's check it. Now our prefix is com only. And now it is checking with this word compound, so it's correct. Until here there is no problem. There is no difference. Now, after that, it wants to check the 4th position. the P with the fourth position of the prefix, but our prefix only has 3 characters. So, of course, it is invalid. We cannot access the fourth character of the prefix because it is not there. This actually crashes the program because we try to access something in the prefix string which is not there. It means that our code is not complete. When our prefix is only 3 characters, why should we continue to check other characters, more than 3 characters? We already know that our common prefixes until here only have 3 characters. There is no point in checking other characters, because at the best condition, we will only have this as a prefix, com. We need to do something here. If our IDX actually grows more than the length of our prefix, we don't need to continue because it already means that our prefix reaches the end of the length of the prefix. It can also happen for the words inside the list. For example, imagine that our prefix becomes 8 characters, but one of the words in our list is only 5 characters. What's the point in checking more than 5 characters? We don't need it, so in that case also we need to check if the IDX is growing more than the length of the word itself, the word that we are checking now. These 3 conditions, any of these 3 conditions, can stop our process. So it should be or. Here, any of these conditions can stop our process. And then we need to update our prefix. You can check this again. Just imagine, just think about the different scenarios that can be. Okay, let's try and run this. What is happening here? IDX? Yeah, this is not correct. Yeah, now it's okay, everything is okay. We can see that exactly it is shrinking and it reaches only 2 characters. But here we are actually showing the prefix in each iteration. If we just want to have the final answer, we can go back and go out of the whole loop and just show the final results. And that's the solution to this problem. Let's move on to the last problem, checking whether a number is a palindrome or not. A palindrome number is a number that reads the same forward and backward. In other words, if you read the number from left to right or from right to left, it stays the same. That is exactly what we want to check. We will take an input number and determine whether it is a palindrome or not. So, how can we solve this problem? Before that, you can find this problem on LeetCode and similar websites. And the problem statement there already explains the idea very clearly. Here we have a function that checks whether the input value x is a palindrome or not. For example, 121 is a palindrome number because it reads as 121 from both directions. But negative 121 is not a palindrome number because when reversed, it would look like this. And the last example, 10, is also not a palindrome number. So these are the kinds of input values that we need to consider. To start solving this problem, we can simply take one sample number for ourselves. I think this one should be a palindrome number. So let's use it and test the idea. One of the simplest ways is to convert the number to a string. So we can write a star of x. The output will be the string version of the number. If we print it, of course it looks the same, but now the value is a string. Once we have the string, we can reverse it very easily in Python. We can calculate the reverse of str of x because now we have the string itself. And with slicing, we can reverse it directly. This will give us the reversed version of the string. To test that, let's use a number and print both values so we can check the reversed string. Yes, let's try it. This is our original number, and this is the reversed one, so it works. Now, the only thing we need to do is check whether the original string is equal to the reversed string. If we reverse the number and it is still equal to the original, then it means the number is a palindrome. So in that case, we return true. Otherwise, if it is not equal, we return false. We can remove the extra print. We don't need it anymore. Yes, for this number, it is not a palindrome, but 121 is a palindrome. And even for a longer number, we can clearly see that the result is correct. Okay, so now let's try this on the website and see whether it solves the challenge. Here we already have the function, and we just need to make sure the indentation is correct. Also, instead of printing, because we need to return a value, we return the result. Then we run it. It checks a few simple test cases. We can see that it is not working for one example because we did not consider negative numbers. That is easy to fix. If x is smaller than 0, then we simply return false. Right? Okay. For 10, it is also not working. So why is that? Yes, here we forgot to write false. Yes, now it is correct. For case 1, this one. For case 2, this one. For case 3, this one. Now we can submit our solution and see where we stand among all the people who solve this problem. We can see the runtime, and there are many people who even get 20 milliseconds for all the test data. Here is our place. We are actually at 3 milliseconds, which means we are better than 88% of the programmers. In the memory comparison, we are here, so we use more memory, but some others use less. Okay? This is the first way of solving the problem. Okay? We solved the problem, but there is something interesting in the description. It asks, could you solve it without converting the integer to a string? It seems they already know that converting the number to a string and reversing it is the easy way. They want to know whether we can solve it without turning the number into a string. So let's try. Here we want to use only calculations. How can we access the individual digits? Let's see. If we want to access the left part of the number, we can simply divide it using integer division by a number like 10. If we do that, the output becomes this part, simply because division by 10 removes the last digit. If we use 100, it becomes this part, and so on. What about the other side? Can we access this part? It should be possible to get the right part too. We can say, okay, if we take the left part and multiply it by 1000, for example, what do we get? We get this number. But if we subtract that value from the original number, then we are left with this part. So easily, we can separate the left and right parts. You can see that we do not use any strings here. This is all just number calculation. String manipulation is easy, but calculation is pure number handling. Okay, so if we define a variable like d just to represent a digit position, instead of using these fixed numbers, we can use powers of 10. So instead of hard-coding values, we can write 10 to the power of d. Just for simplicity and clarity, we use this form. We should get the same result. But now, by changing d, we can easily cut different parts of the number. Yes, straightforward. Now we can say that we want to take this part first, the right side, and from that right side, just take the leftmost digit. How can we do that? For that, we can define digit as the lower part of the right side and then divide it by one power lower. For example, if D is 5, then here we divide by 10 to the power of 4. If we divide this number by 10,000, then we get only 1. If we have 673 and divide by 100, then we get only 6. So let's try it. Okay, of course we cannot see it because the digit itself is not printed. Yes, so we cut the right part. And then from that right part, we again cut its right side. And that leaves us with the digit. You can see that by choosing digit number 3, we catch digit 3, the third digit. If we choose 6, we catch the sixth digit in the number. So this is the way we can access any digit. Okay? So now we have the tool. We know how to access individual digits of the input number. So first of all, we need to know how many digits the number has. How can we do that? If I divide this number by 10, we get this. Let's use integer division. If I go further, it cuts more and more. And if I keep dividing by larger powers of 10, eventually we reach 0. It means that once division gives us 0, we have gone beyond the number of digits. So just before that, we had the digit count. What we can do here is run a loop over a safe range. Since the number range is limited, we can just use 12 or 13 steps for safety. If, while increasing c, we divide the number by 10 to the power of c and get 0, then we break the loop. We do not need to continue because we have already reached the point where the division becomes 0. At that moment, c tells us the number of digits. Let's print c and check. The output is 9, which is the number of digits. If we use another number, for example 1, 2, 3, 4, 5, then it gives us 5. So yes, it is correct. Now C shows the number of digits. For checking whether the number is a palindrome, we can start from the left and right at the same time. For that, we use a loop. In this loop, we only need to go until half of the digits, because we only compare pairs. If we have 9 digits, we only need 5 steps. So we can divide C by 2 and then add 1. 9 divided by 2 is 4, plus 1 gives us 5. So now we have 5 steps. Okay, let's remove this extra part. Now, we just focus on the left side of the number. For simplicity, we can define a function. Get digit from x at position d. We move this logic into a function. Here we have d, here we have x. We define the calculation and then just return the digit. Now let's print the digits we get. We say get digit of x and d. Yes, we just want to check that the function works correctly. Something is wrong, so let's print d and digit together. Okay, now it shows d. And we can see that the first issue is that it starts from 0. Since the number of digits is 5, the range goes from 0 to 2, which is not what we want. We should not start from 0. Our digit positions start from 1. So that is the problem. The range should start from 1. Let's fix that and try again. Okay, now it goes over the correct digits. We have 5 digits, but it still stops too early. Of course, because 5 divided by 2 is 2, and then 3. But the 3 itself is not included. So we need one more step. Now, it goes through 5, 4, and 3, which means it covers the first, second, and middle digit from the right side. In this way, it calculates the digits we need. At the same time, in the same loop, we can move to the other side as well. When we calculate the first digit, we can also calculate the 5th digit, then the 2nd and 4th, and move inward. Since we know the number of digits c, we can say c minus d plus 1. If c is 5 and d is 1, then the result is 5. So that gives us the last digit. Let's try it and check whether it is correct. Instead of d, we use c minus d plus 1. Let's see. In every step, we now get the first digit and the fifth, then the second and fourth, then the third. Can you see that? In this way, we know it is working properly. Instead of printing, we can use variables. Let's call them right digit and left digit. That is clearer. This one is the right digit and this one is the left digit. Then after that, we compare them to see whether they are equal. Is that okay? Let's test it. If they are the same, everything is fine and we continue. But what we are really looking for is a difference. If at any point the digit from one side is not equal to the digit from the other side, then the number is not a palindrome. That is the idea that makes the logic easier. So we can define a result variable. For example, result equals true. Then if we find any mismatch, the result becomes false. Once that happens, we do not need to continue because we already know the number is not a palindrome. So we break the loop. Then at the end, we return the result. Let's try it on this number. The result is false, of course, because it is not a palindrome. Now let's try our original number and see whether it works. Now it gives true, which means it can detect it correctly. What about negative numbers? I think we did not check that. Negative numbers should be false. Yes, that is correct. So you can see that, again, we solved the problem without using strings, only with number calculations. Okay? Now let's try this algorithm on the website and see what result we get. Remember, with the first solution, we were at 3 milliseconds and better than 88% of people. So let's see. We put the code here. Just remember to use the correct indentation because Python is very sensitive to that. We paste the code and instead of printing, we return the result. Let's first run it on the simple test cases. Okay, we have a problem here. What is the problem? Yes, the indentation is not correct. You can see the indentation error, so we fix that. Now, for case 1, 121, or the negative numbers, even though we did not explicitly handle them here yet, the algorithm itself is mostly working, and case 3 is also correct. So, let's submit it and run it on the full set of test cases. Something is wrong. Okay, we can see that for negative 1 it does not work. That means we need to add a very simple condition. If x is negative, return false. That's it. Let's try again. Yes, and submit. Yes, now it is correct. But you can see that because of all the calculations we do, now we are almost at the end. We are only better than 5% of people. In the memory comparison, we are not too bad, but in runtime, we are near the bottom. Okay, we can see that our runtime is 41 milliseconds, just better than 5% of people. So how can we improve this code? How can we reduce the amount of calculation? One thing we can notice is that we keep calculating many powers of 10. Is it possible to get rid of those repeated calculations? They are constants, and also the range is limited. So I can define a list for simplicity. I do not calculate them every time. I just write 10 to the power of 0, then 1, then 2, then 3, then 4, then 5, then 1 million, 10 million, 100 million, 1 billion, and 10 billion. Just let me check that everything is correct. This is 1 million, this is 10 million, this is 100 million. Yes, now we have all these numbers ready without recalculating them. Here, If we want 10 to the power of c, we can simply say p at c. It directly gives us the value we need. We can do the same replacement in the other places too, just to show that we can always try to improve code by thinking differently. Here, this one and this one. Do we need anything else? All the powers of 10 are now replaced. So let's try to make it work properly. Okay, something is wrong here because it says, what is that? Ah, here we have a parenthesis. We do not need. Let's remove it and try again. Now, the three simple cases work. We again have this larger set of test cases, around 11,500 of them. So let's submit and check the performance. And we can see that the result is still not very good. In fact, even worse, 47 milliseconds this time. Okay, let's try it again, because sometimes the runtime changes. Now, it is 55 milliseconds. So you can see that the runtime is not perfectly reliable from run to run. But it still shows that this code is not improving. In theory, because we removed some calculations, it should have become faster. Let's think about another way. Instead of trying to find individual digits directly, we can do something else. Let's go back to our code and try this. We cut the number from the right side and build a new number in reverse, but only until the middle. Let's see what happens. If we divide x by 10, we remove the last digit, and the remainder of division by 10 gives us that last digit. So, we can take that digit and build a reverse number from it. Let's try that. We start from 0. Then, while x. Okay, we do not know the exact condition yet. But for now, let's just make it true and think about the condition later. We want to build the reversed half. To build it, if we already have 3 and then get 7, we multiply the existing reverse by 10 and then add 7. So reverse half becomes reverse half times 10 plus x mod 10. Then we remove that last digit from x by dividing x by 10. In this way, x keeps shrinking. Because x is shrinking and reverse half is growing, there will be a point where x becomes smaller than reverse half. At that moment, we know we have reached the middle. Let's print both x and reverse half and see how it works. We can put x on the left side so it is easier to read. We do not need this other print for now. Okay, you can see it here. First, we catch the 3 in reverse half. Then, next time, we multiply 3 by 10 and add 7. At the same time, x has already lost that last part. So x keeps shrinking and reverse half keeps growing until reverse half becomes greater than x. At that moment, we stop. In this way, we only process half of the number. We do not need to think about all the digits. Now, what should we do after that? We can say, check whether x is equal to reverse half. That works when the number of digits is even. Let's test it with 1221. You can see that when we reach the middle, the reverse half is equal to the remaining x. That works for even length numbers. But there is another possibility. If the number has an odd number of digits, then reverse half will have one extra digit in the middle. We do not need that middle digit. So in that case, we compare x with reverse half divided by 10. If they are equal, then it is still a palindrome. That works for odd length numbers too. But what about numbers like 10 or 100? Here we get a wrong result. Something is wrong. The reason is that the last digit is 0. In such cases, our calculation is not enough by itself. So we need to manually handle those exceptions. If x is less than 0, just return false. If x is 0, that is okay. But if x is greater than 0 and ends with 0, then it cannot be a palindrome because the first digit cannot be 0. So these are special cases we need to handle manually. For the rest of the numbers, the logic works fine. Let's clean this up. We do not need that part anymore. And here also, we just want to keep the function itself. So remove this, copy the core logic, go back and try it again. Make sure the indentation is correct. We fix the while loop, and then this is the result. Let's try the 3 simple cases. It works. So now, let's submit it. Okay? Now we can clearly see the improvement, a very significant improvement. From around 40 or 50 milliseconds, we reduced it to 13 milliseconds. And now, we are better than 23% of people on all the test cases. So you can see that we can solve one problem in different ways. And each solution has its own strengths and weaknesses. For this problem, we started with string manipulation. That solution was very fast, very easy, and very simple. If we do not want to use that solution because of the challenge requirement, then we can solve it in other ways. We can access individual digits and compare them, or, like in this final solution, we do not even think about the digits directly. We start from the right side, collect digits, build the reversed half of the number, and then compare it with the remaining half. That's it. So these were our first 3 practical coding problems in Python. And as you can see, the important part was not just coding, but learning how to think through the problem, test different ideas, and improve our coding step by step. If you like, in the next videos, we can continue to solve these kind of problems and build a real programming thinking together. If this helped you, please make sure to like the video and subscribe to the channel. Thanks for watching, and I'll see you in the next video.